चलें ठीक है, अभी रिकॉर्ड हो रही है। अच्छा, सो फर्स्ट प्लस सेकंड ये डेटा बुकलेट ने खोली थी, नहीं खोली थी अभी।
So the values are 502 and 966.
500
502 and 966.
अच्छा 966 ठीक है। फिर ये electron affinity. Be very careful about electron affinity. But remember, electron affinity is always given for. Sometimes it's given for 2 electrons, लेकिन फिर वो explicitly they tell you that it's for 2 electrons. लेकिन यहाँ पे if it says sulfur atom, then sulfur atom right now is only मतलब ये -200 में it's only gaining 1 electron. Sulfur -1, that's where it's gaining the second electron. ठीक है। This is S-1 trying to gain 1 electron to form S-2. और इससे ऊपर वाला जो है सल्फर एटम की जो होगी दैट विल बी सल्फर एटम गेनिंग 1 इलेक्ट्रॉन टू फॉर्म S-1. So you would have to take both of them. So -200 plus there is 640 and plus there is lattice energy. Now in this case the enthalpy of formation is also given, that's given as -460. So ये first वाली value that's also with you.
Sir, we get -2827.
So now just remember when you calculate lattice enthalpy, there's a lot of chances of making mistakes. ठीक है, the first thing is you might get the moles wrong, जो कि इस वाले केस में तो issue नहीं है. But the other thing is you might also get this simple calculation wrong. तो ये थोड़ा सा आइडिया लगा लेना कि it's usually around -2000, -1000 से -5000 तक होती है, लेकिन most of the time the answer is somewhere in the -2000 range. अच्छा, this one was an easy one. इसके अंदर देख लेते हैं next paper के अंदर where's the
सर एंथैल्पी चेंज ऑफ एटमाइजेशन सर वो 1 मोल के लिए होती है सर, अगर इसमें मल्टीप्लाई बाय 2 होगी, अगर 2 मोल हो कोई भी सबसे जैसे बेरियम है या 2 मोल हो तो होगी।
हाँ, तो फिर 2 से करोगे ना, वो ठीक है बिल्कुल। अच्छा, फॉर एग्जांपल दिस वन, ठीक है, ये क्वेश्चन थोड़ा सा मुश्किल है बिकॉज दिस इज नॉट typically, remember there's a very little bond neighbor cycle is a Hess cycle, ठीक है। तो now okay, use the data in the table and from the data booklet to calculate the enthalpy of formation of OHNs gaseous. ये उसने कहा है। अच्छा, now this question is कि उसने it's not really about the bond neighbor cycle directly. अच्छा, उसने कहा you might find it useful to construct a bond neighbor cycle. So enthalpy of formation, it's this one. You're basically trying to figure out this path. Now, तो उसने कहा कि bond neighbor cycle बनाओगे ना तो it might get easy, ठीक है। It might be, उसने hint दी हुई है, ठीक है। It's useful to construct a bond neighbor cycle. So we're going to go for a bond neighbor cycle और देखते हैं कि how is it really going to be useful. So enthalpy of formation is given for MgOH2. So I'm going to try and make a bond neighbor cycle for that. Enthalpy of formation would be elements Mg and O2 and H2, ठीक है। They're trying to form MgOH2, right? And MgOH2 is a solid. So this is what's happening. This is a solid. 1 mole substance is formed from its gases or from its elements in the standard states. So oxygen is a gas, Mg is a solid. So this value is given, that's -925. So we're going to start constructing. Ab kya diya? What else is given? Enthalpy of atomization of Mg is given. So why don't we atomize Mg? So it's going to become Mg gaseous. Okay, and there's balanced. The first one is balanced. Remember to balance the equation O2 plus H2. So these two are gaseous. So then you have so the first one we connected the first one, that's plus 148. Okay, this one atomization of Mg solid turning into Mg gaseous. उसके बाद क्या होगा? उसके बाद what's going to be there is you've got the last one, lattice energy of MgOH2 solid, that's -2993. ठीक है, फिर से देख लो, mostly the value is within that particular range. So what's in the lattice enthalpy? Lattice enthalpy is when 1 mole of ionic lattice is formed from its gaseous ions. The gaseous ions are the Mg2 plus, and the other gaseous ion in this case is OH ions. Okay, both of them are
सर
the
आप इनकी
gas.
फर्स्ट आयनाइजेशन एनर्जी वगैरह नहीं लिखेंगे?
कौन सा?
इनकी आयनाइजेशन एनर्जी आप नहीं लिखेंगे सर, ये मैग्नीशियम और ऑक्सीजन हाइड्रोजन की?
नहीं, अभी तो आयनाइजेशन एनर्जी पे तो मैं आया नहीं हूँ. ठीक है, अभी हम क्या कर रहे हैं?
यस, लैटिस सर. सर लेकिन लैटिस एंड में नहीं होती?
कौन सा?
ये लैटिस वगैरह सर एंड में नहीं होता?
हाँ, एंड पे होता है, उसका मैंने एरो गलत बनाया हुआ है. ठीक है, एरो इज द अदर वे अराउंड. तो वो एंड पे ही है ना, मैंने कौन सा पहले बनाया?
ओके सर.
वो बीच वाला ये मिसिंग है ना अभी, साकिब. ठीक है,
अंडरस्टूड सर. यस सर.
अच्छा, वो तो अभी मैंने सिर्फ वो चीजें ऐड की है जो उधर लिखी हुई हैं. ठीक है, उसने एटमाइजेशन ऑफ एमजी किया था, मैंने एटमाइज कर दिया, एमजी सॉलिड से गैस कर दिया. ठीक है, द अदर थिंग वाज अच्छा, द अदर थिंग वाज यू वर गिवन लैटिस एनर्जी, तो वो दिया हुआ है -2993, राइट? अच्छा, एरोस की डायरेक्शन का भी ख्याल रखना है, बिकॉज यू कैन गेट द एरो डायरेक्शन रॉन्ग और फिर पूरा क्वेश्चन ही गलत हो जाएगा. ठीक है, इतनी एफर्ट, और मार्क्स भी इतने ज्यादा नहीं होते, यूजुअली 3 मार्क्स होते हैं. अच्छा, सो -2993. अच्छा, नाउ द मिसिंग पार्ट इज दिस वन. अच्छा, कैलकुलेट हमने क्या करना है, यहाँ पे हम इसको ले आते हैं. व्हाट वी नीड टू डू इज, रिमेंबर के द फोकस इज ऑन दिस थिंग. It's trying to figure out this equation. Okay, H2 plus O2 and forming OH ions, right? The first thing is कि Mg का कोई काम नहीं है, so I would try to convert Mg to Mg2 plus. Okay, that's out of the way. तो Mg को ionize कर लेते हैं. So you now have, after ionizing Mg, you have Mg2 plus gaseous ions, O2 को gas and H2 gas. They should remain as it is. ठीक है, हम यहाँ तक आ गए. आयनाइजिंग एमजी ये कहाँ से मिलेगा हमें? ये हमें डेटा बुकलेट से मिलेगा. सो आई जस्ट हैव अ लुक एट द डेटा बुकलेट. तो एमजी इज ओवर हियर, इट्स 736 एंड 1450. ये दो वैल्यूज हैं. सो 736 प्लस दिस इज 1450. खैर यहाँ तक हम आ गए. तो अब ये बीच वाला पार्ट मिसिंग है. ठीक है, क्योंकि जो कुछ हमें मिल सकता है डेटा बुकलेट से, I've added everything. Now the only thing left is this middle part. So what is this middle part? बाकी सारी चीजें हमें पता है. अब उसने दिया हुआ था, he had given you oxygen plus hydrogen forming OH ions. ठीक है, so we have exactly the same thing is happening over here. There's oxygen plus hydrogen and they're turning into OH ions. Mg को कुछ नहीं हो रहा है इस पाथ के अंदर. Mg2 plus पहले ही Mg2 plus gaseous, and over here it's still Mg2 plus in gaseous state. So nothing is happening to Mg at the moment, at this point. तो ये वही equation है. It's O2 plus H2 turning into 2 OH ions. और plus बीच में 2 electrons करना पड़ेगा क्योंकि 2 OH negative ions. ठीक है, 2 negative ions would only be formed if something gains 2 electrons. So that means there are 2 electrons being gained over here at this point. तो ये वो path है जो हमने figure out करना है. This is our unknown, this is our x. So one path is equal to the other path, और फिर solve inequality बना लो. So one path is this one, the first one, that's -925, and that's equal to this entire other path, so that's +148. Equal करना है, ठीक है. So it's going to be equal to +148, and then you have +736, plus you have 1450, plus ये x unknown path, और फिर -2993. Now remember, जो भी वैल्यू आएगी ना x की, उसको n में डिवाइड बाय 2 करना है, क्योंकि उसने जो आपको कहा था ना, he had asked you to find it for 1 OH ions. We're figuring out the same reaction but for 2 OH ions.
Sir, I think we get -133 kilojoules per mole.
For x, I mean that's for x or for this thing, for this equation, right?
No, sir. That's minus 266, and then when you divide by 2, you get minus 133.
Okay, so you're getting minus 266, but that's for 2 OH ions. And over here you had to do it for 1 OH ion. So now the thing about this question is that this is not exactly a Born-Haber cycle. It's similar to a Born-Haber cycle, लेकिन इस पॉइंट से यहाँ तक they're just jumping, ठीक है, उसने डायरेक्ट जंप मार दी है कि मतलब you just have to identify this कि oxygen plus hydrogen and they all of a sudden turn into OH ions. मतलब Born-Haber cycle में you do this in steps. You पहले उसको you break the bond, H2 का bond break करते हो, फिर उसको ionize करते हो, whatever you do that in steps. Over here is क्योंकि उसने कहा वही यही था कि H2 और O2 को डायरेक्टली OH ions में कन्वर्ट करना है, so ये पूरी जंप आपने डायरेक्ट कर ली, ठीक है?
सर
क्लियर है?
ये हम मोनोएटॉमिक नहीं करेंगे ऑक्सीजन और हाइड्रोजन, यहाँ पे 2 मोल्स है ना।
वही इशू है, वो नहीं करेंगे क्योंकि the thing is कि उसने वो सारे बीच में स्टेप्स निकाले, वो कहीं नहीं था, उसने बस कहा था कि ऑक्सीजन और हाइड्रोजन को डायरेक्टली OH आयंस में कन्वर्ट करना है, उसकी एंथैल्पी चेंज, यू हैव टू मेजर दिस एंथैल्पी चेंज, राइट? समझ रही बात? तो मतलब वैसे तो बॉन्ड है, वैसे तो बॉन्ड, हाँ
सर आप बोल रहे, सॉरी सर।
नहीं मैं वही कह रहा हूँ कि इसके अंदर यू एक नॉर्मल बॉन्ड एबल साइकिल के अंदर ना यू ब्रेक द बॉन्ड्स, उसको स्टेप वाइज चलते हो ना आप, ठीक है? इसके अंदर इशू ये कि उसने कहा ही नहीं है स्टेप्स निकालने का, उसने बस कहा है कि O2 और H2 को डायरेक्ट OH आयंस पे कन्वर्ट करना है, तो क्या एंथैल्पी चेंज होगी, ठीक है?
सर इक्वेशन में तो उसने हाफ किया हुआ है।
किसमें?
आप इक्वेशन दिखाएंगे?
यस,
इधर उसने हाफ H2 और हाफ O2 लिया है ना, तो लाइक उसमें मोनोएटॉमिक लिया ना, एक OH माइनस आयन के लिए, और हमने 2 OH माइनस आयंस के लिए लिए, तो हम
इसलिए हमारा आंसर जो आ रहा था -266 आ रहा था ना, इसको हाफ करना होगा।
लेकिन हम अपनी साइकिल में मतलब O2 और H2 को आधा नहीं कर सकते, एंड देन वी कैन डायरेक्टली जस्ट
नहीं, वो साइकिल में कर सकते हो, हाफ कर सकते हो, बिल्कुल कर सकते हो, लेकिन फिर उसके लिए सब हर जगह हाफ होना पड़ेगा, फिर ये सारी वैल्यूज को हाफ करना, मतलब या तो आप सारी वैल्यूज को फिर हाफ करो, क्योंकि आप इस वाली इक्वेशन में भी O2 1 है ना, हाफ O2 होना चाहिए ना।
सर सारी इक्वेशंस को क्यों करना पड़ेगा? ये mg के लिए नहीं है 736 + 1450, और फिर जो नेक्स्ट होगा वो सिर्फ,
लेकिन O2 को अगर हाफ करोगे, यहाँ पे अगर हाफ करोगे आप, ठीक है, तो ये बैलेंस्ड आ रहा है ना, ये O2 कहाँ से आ रहा है, यहाँ से आ रहा है ना, तो इधर भी हाफ होना चाहिए, ठीक है? तो वो फिर हर जगह ही हाफ होगा ना, मतलब ये सारी इक्वेशंस है ना, यहाँ से आप यहाँ आए हो, फिर यहाँ से आप यहाँ आए हो, ये सारी इक्वेशंस है ना, तो अगर आप यहाँ पे हाफ O2 करोगे तो उससे पहले भी हाफ O2 होगा, और फिर उससे पहले भी हाफ O2 होगा। अच्छा, अगर हाफ O2 होगा तो यहाँ पे भी हाफ O2 हो जाएगा, तो Mg ऑटोमेटिकली आपको हाफ करना पड़ेगा बैलेंस करने के लिए।
जी सर।
मतलब ये पहली इक्वेशन ही, अगर इसमें O2 हाफ रखना है तो फिर वो पूरी इक्वेशन को ही आपको हाफ से मल्टीप्लाई करना पड़ेगा ना, तो Mg भी हाफ हो जाएगा, ठीक है?
जी सर।
अच्छा, नाउ तो ये बस इस तरह का एक वो क्वेश्चन था, और भी देख लेते हैं जस्ट क्विकली वन
सर। ये इसमें आई हैव वन डाउट सर, इसमें आपने एंथैल्पी चेंज ऑफ एटमाइजेशन ऑफ मैग्नीशियम क्यों ऐड किए सर? 148
एंथैल्पी चेंज ऑफ
एंथैल्पी चेंज ऑफ एटमाइजेशन ऑफ मैग्नीशियम सर, 148 वैल्यू जो आ रही थी।
नहीं, क्योंकि साइकिल कंप्लीट करनी है ना, वरना अगर यहाँ पे Mg एटमाइज ना होता, मतलब यहाँ पे क्या है, क्योंकि मैंने ये पाथ क्रिएट करना है ना, तो Mg सेम रहना चाहिए ना, Mg यहाँ पे 2+ है, तो Mg यहाँ पे भी एग्जैक्टली सेम स्टेट में है ना, तो इसका मतलब है कि इस पर्टिकुलर पाथ में Mg का कोई रोल नहीं है।
लेकिन सर उसकी आपने एंथैल्पी चेंज ऐड की हुई है पूरी वैल्यू में 148 से,
तो Mg
इक्वेशन में
Mg गैस पे आओगे, फिर Mg 2+ में आओगे, मतलब यहाँ तक पहुँचना है ना।
लेकिन सर इक्वेशन तो ओनली ऑक्सीजन और हाइड्रोजन के बारे में है।
हाँ, तो लेकिन बॉर्न-एबल साइकिल में तो सब कुछ ही आ रहा है ना, जो उसने दिया हुआ है उसके अंदर Mg आ रहा है ना, तो अब Mg को तो बीच में से नहीं निकाल सकते एकदम से।
तो सर उसने जो एनर्जी दी हुई है, लेटेस्ट एनर्जी वगैरह, तो उसमें सर फिर खाली ऑक्सीजन और हाइड्रोजन की वैल्यूज नहीं आएंगी?
नहीं, ये जो लैटिस एनर्जी है इसमें Mg भी है और OH आयंस है, वो मिलके ये आयनिक लैटिस बना रहे हैं, सो इट्स -2993। तो वो सिर्फ और सिर्फ ये जो पाथ है ना, ये वाला पाथ, इसके अंदर mg का कोई काम नहीं है,
यस सर।
ठीक है। वो बाकी हर जगह mg का रोल है, मतलब mg O2 के साथ मिलकर ये बना रहा है -9 × 25 और mg OH2 बना रहा है, बाकी हर जगह mg का रोल है। सिर्फ बीच में ये जो पाथ था ना, ये वाला जो x जिसको हमने कहा है,
यस सर।
दिस इज द पाथ वेयर mg is playing no role। वहां पे सिर्फ क्या हो रहा है कि ऑक्सीजन एंड हाइड्रोजन आर कंबाइनिंग टू फॉर्म OH आयंस। क्लियर है?
यस सर, थैंक यू सर।
अच्छा खैर, बाकी ये सेम वही बॉन्ड नेबर साइकिल, उसने लेबल जल्दी से लेबल कर लेते हैं, उसने लेबल करने को ही कहा है। ये बॉटम के ऊपर दिस इज एंथैल्पी ऑफ फॉर्मेशन, ये उसने एनर्जी वाइज उसने ड्रॉ किया हुआ है। गेन ऑफ एनर्जी इज पॉइंटिंग अपवर्ड्स, लॉस ऑफ एनर्जी इज पॉइंटिंग डाउनवर्ड्स, ठीक है। सो वरना इट्स द सेम हैज साइकिल। अच्छा, एनीवेज यू हैव गॉट एंथैल्पी ऑफ फॉर्मेशन, एलिमेंट्स टर्निंग इनटू एन आयोनिक सॉलिड, ठीक है। अब इधर से वो ऊपर जा रहा है, दिस इज mg solid turning into mg gaseous, तो ये enthalpy of atomization of mg है। अच्छा, after that you have Cl2 breaking into two Cl atoms, so that's enthalpy change of atomization of Cl, but that's multiplied by 2। फिर क्योंकि दो Cls हैं, ठीक है, फिर वो दो Cls इलेक्ट्रॉन्स गेन कर रहे हैं, so that's electron affinity of Cl, and again multiplied by,
Sir, this
yes,
one would be first ionization of energy of magnesium, right?
हाँ सॉरी, नहीं इसमें दोनों हो रहे हैं, both of the, नहीं sorry, this is the first, yes, I mean nothing is happening to Cl, ठीक है, I'm wrong। इस वाले पाथ में, ठीक है, I just felt कि Cl was gaining electrons, it's Mg that's losing, Mg is turning into +1, so that's the first ionization energy of Mg, और उसके बाद this is the second ionization energy of Mg, and then your Cls are gaining 2 electrons, so forming 2 Cl ions, so that's electron affinity of Cl times 2, and this over here finally is your lattice energy, ठीक है, so that's your complete cycle। अच्छा, just hold on one, I'll be back in 30 seconds। अच्छा चले, बाकी
Sir,
सारी, yes,
sir, wouldn't delta H2 be bond energy for chlorine?
that is the bond energy, but that is the, I mean you could label it both, I mean it's basically Cl2 turning into two Cl atoms, right?
Okay, ठीक है.
So that is the bond, that is 1 times the bond energy of Cl, because you're just breaking one bond, right?
Yeah.
And you can, because you're making gaseous atoms from the element, so you can call it the enthalpy of atomization of Cl, but times 2।
Okay, ठीक है.
अच्छा, बाकी this is exactly the same, ठीक है, no different,
Sir,
and
can
this
we do
one,
a whole past paper?
hmm?
Can we do a whole past paper instead of skipping through?
नहीं, we, I'll do that, ठीक है, I'll do that, लेकिन पहले I'll just go through these questions first, just 1 second। ये बस skip कर ले, एक बस quickly ये Faraday constant के कर ले। Faraday constant का तो easy है. Mariam, organic synthesis का I'll just explain very quickly. ठीक है, organic synthesis.
Okay.
Faraday constant के बहुत थोड़े से simple questions वो हम कर लेंगे बाद में. अच्छा, the only thing about organic synthesis that you should know, hopefully this opens. The only thing that needs to be known about organic synthesis is basically organic chemistry, nothing different. Functional group, etc., everything is pretty much the same. Now, the only thing that's need to be understood is when you're trying to make an organic molecule, you plan some routes. Okay, how to make that organic molecule, which you probably know. Okay, for example, if you want to convert a nitrobenzene into phenylamine, you need 10 plus concentrated HCl. So you know, if you want to convert a benzene into bromobenzene, you would add Br2 plus FeBr3 as a catalyst. So you know all the routes. If you want to turn an alcohol into primary alcohol into a carboxylic acid, you would oxidize it. Okay, so you pretty much know all the routes. But you also need to understand that there would be different functional groups. But these are things which have to be kept in mind. Okay, what type of yield would you get? For example, if you want to convert an alkane into chloroalkane, free radical substitution would not be a good idea, because like if you want to convert propane into 2-chloropropane, free radical substitution would not be a good idea, because free radical substitution would result in a number of different products, because free radical substitution is uncontrollable, and any number of hydrogens could be substituted. Okay, remember 2-chloropropane where you just need 1 chlorine at the second position. Now in free radical substitution, you would probably get a lot of chlorines at many different positions. So you're not going to get the right product. Okay, so you must have some idea of what type of conditions should you use. For example, if you want to oxidize an alcohol, primary alcohol, into an aldehyde, then you would have to prevent it from converting into a carboxylic acid. So, distillation use करते हो, you change the condition. So, different. Every reaction has some particular problems associated with it, which you have studied in organic chemistry already. ये तो खैर वैसी जनरल बातें. अच्छा, these are now this one is important, that when you're trying to plan, if you in an industrial practical setting, if you're trying to plan an organic product, one thing that needs to be understood is that every molecule has many different isomers, excluding structure. I mean, even molecules that look exactly the same, they have optical isomers, they have geometric isomers, and they behave differently. Okay, so if you're trying to make a medicine, then it's always the right type of medicine that works. The other one causes side effects. So for example, if I can draw over here just a second. So if I have a molecule, and the molecule is like, it's a medicine molecule, and it's something like this. It's OH and a Cl and a CH3. Now I can make this molecule very easily. The problem would come that this carbon over here is chiral. Okay, it's chiral, and it would result in 2 different enantiomers, and you'll get a racemate mixture. Okay, so you have OH and you have Cl and you have CH3, and there's going to be a mirror image that's going to be the opposite. And this one works. The mirrored version probably causes side effects. You get the mirrored version where the OH and you have the Cl coming out of the page and the CH3 going into the page. So this one is going to cause side effects. The सारी problem ये कि it's pretty hard to actually figure out exactly how to make the right type of optical isomer. And it's kind of a big problem, very difficult in the lab. It's very difficult to obtain the right type of enantiomer or geometric isomer or whatever stereoisomer we're talking about. Every molecule is going to result in a number of different products. Even structural isomers, for example, agar aap, let's say you have a butanol molecule, right? And you want to turn it into an alkene. Now it's a simple reaction, right? Okay, it's a dehydration reaction. So you have butan-2-ol, तो इधर से OH निकालो और साथ वाले से H remove होगा, and it would turn into an alkene. Now the thing with that would be कि you'll get a number of different alkenes. Why a number of different alkenes? के हो सकता है H ये वाला चला जाए, so it would be a butanene molecule, या फिर हो सकता है कि so that's one version, or it could be possible that the H is gone from the left side, so it would turn into a butene molecule. Now if it turns into a butene molecule, तो उसके फिर अलग मसले हैं, क्योंकि उसके फिर दो ज्योमेट्रिक आइसोमर्स होंगे, तो उसकी अलग दो वर्जन्स होंगी. The two versions would be कि one would be a cis version, the other one would be a trans version, where ये वाली जो दो sides हैं ना, they are flipped around. ठीक है? So the thing is, it's kind of really difficult to actually predict in a lot of reactions the product of the reaction. So it's going to have a poor yield. Okay, let's say आपको किसी ने कहा था कि but1ene ही बनाओ, लेकिन अब ये भी बन रहा है, ये भी बन रहा है. So मतलब अगर हम let's say equal probability लगाते हैं तो 30% yield होगी. That's a very bad yield. ठीक है? Is this clear?
Yes, sir.
और इसी तरह अच्छा, इसी तरह free radical substitution का बताया था कि so you must know कि which reactions, if you have free radical substitution and you have all these hydrogens and you've got chlorine plus UV light. अब question में या industrial setting के अंदर आपको you're supposed to make 2 chloropropane. You want a Cl at this point only. But with chlorine plus UV light, you're not going to get Cl at that point. That's going to be very, very difficult to get Cl at that point. क्योंकि Cl यहाँ पे भी substitute हो सकता है. It could be, all of them could be Cls. ठीक है? So you get different products. And again, the yield is going to be it's going to be a pretty bad yield. तो आपको ना हर रिएक्शन के बारे में थोड़ा सा आइडिया होना चाहिए कि हर रिएक्शन के अंदर क्या क्या मसले हैं. ठीक है? क्योंकि जो प्रोडक्ट होगा ना, काम सिर्फ एक ही कर रहा होगा सही. ठीक है? Even if optical isomers are being formed, there's only one right optical isomer that's going to work. All the others are going to cause side effects. So
how do we know which one is the right product?
नहीं, वो तो आप एनएमआर स्पेक्ट्रोस्कोपी और इंफ्रारेड, उससे तो आप पूरी मॉलिक्यूल की शेप वगैरह पता लगा सकते हो. सो यू वुड नो कि व्हिच वन इज द वन दैट्स वर्किंग आउट. ठीक है? क्योंकि आपके बायोलॉजिकल मॉलिक्यूल्स होते हैं, दे वेरी शेप स्पेसिफिक. सो मतलब अगर ये वाला मॉलिक्यूल काम कर रहा है ना, लेट्स से दिस वन, I mean, you would be able to know कि lab के अंदर analytical techniques, NMR, infrared, etc. वो देख के you can figure out कि this one is the right one. The other one जो इसकी trans version होगी, that's not the one that's probably causing the side effects. ठीक है? तो ये तो खैर मैंने वही draw कर लिया. अच्छा, बस इतना आइडिया होना चाहिए कि किन किन रिएक्शंस के अंदर, या इफ यू सी अ रिएक्शन, इफ यू सी एनी ऑर्गेनिक रिएक्शन, यू शुड नो कि प्रोडक्ट के अंदर क्या मसला होगा. कि अगर ये मॉलिक्यूल बन रहा है ना, तो ये भी बन सकता है. इट्स द ट्रांस वर्जन ऑफ दैट मॉलिक्यूल. तो इंडस्ट्रियल सेटिंग में दैट्स काइंड ऑफ प्रीटी बैड कि यू गेटिंग मल्टीपल डिफरेंट either structural isomers or you're getting stereoisomers. कि ये चाहिए था, but you're also getting this one. ठीक है? So you don't want that one. अब इसके 2-3 सॉल्यूशंस है. वन इज के नेचुरल जो substances होते हैं, natural substances, especially like medicines made from natural products. Naturally, things they don't they don't exist in different ice. For example, if you look at amino acids and amino acids in the human body, most of the time those amino acids they exist in the right type of chiral shape. They don't exist in both types. So natural molecules or natural substances or natural plants, etc. They medicines that are derived from natural substances, they have less side effects. And the main reason is that in that case, you always have a certain type of chiral that dominates. The other chiral is usually absent in natural molecules. In lab, if you try to make or synthesize something in the lab, the biggest problem is you get other type of optical and geometric isomers which cause harm. So, which is why natural things that are derived from natural products, they're kind of more they have less side effects overall. I said, then you have one second. I said, so when you draw a synthesis route, I mean, you should have some idea of what the problem is going to be. TK, you're not going to be asked a very big question on this, but you must have some idea. Now, this is all about that one optical isomer working better than the other one. But then there are techniques in the lab where you could actually come up with the right type of optical isomers or stereoisomers. Now, for example, there are certain reactions. For example, this is a nucleophilic addition reaction. Now, in a nucleophilic addition reaction, you have one second. So now in a nucleophilic addition reaction, you have a Cn-1 ion that attacks a carbon that's positive. Okay? This is the exact shape of a molecule. This is CH3, this is C double bond O, this is ethanol, CH3, this is C in black and 3 hydrogens. This is C double bond O, and that's your H. So it's when carbon is double bonded, it's sp2 hybridized. That means it's fan shaped. So this is fan shaped. It's flat, it's planar, trigonal planar. So Cn-1 could choose to attack from the top, and if the Cn-1 comes in and bonds from the top, then this particular optical isomer would be formed. And if the Cn-1 chooses to attack from the bottom, then this particular optical isomer would be formed. Now, there's an equal probability of the Cn-1 attacking from both sides. I mean, it could come from the top, it could come from the bottom. So that's equally probable. So you have two different mirror images forming. And so remember this, whenever you have an sp2 hybridized carbon atom, which is trigonal planar, and it's turning into a tetrahedral molecule, remember that both enantiomers are equally possible. Is this clear?
Sir, can you repeat that?
Hmm?
Sir, can you repeat the last part?
No, I'm just saying that when you have a trigonal planar carbon atom, like an sp2 hybridized carbon atom, and that's turning into a tetrahedral molecule, right? So the chances are that that both optical isomers are equally possible. Like the Cn-1 could attack from the top, or the Cn-1 could bond from the bottom. The Cn-1 is attached to it's going to attack the carbon atom. The Cn-1 is a nucleophile. So if it comes from the top, if it comes from the bottom, there are going to be two mirror images, and both of them would behave differently. Okay, Mariam, is this clear?
Yeah.
So remember this point. You'll be asked. I mean, you'll get very small questions on this, and you'll be asked to explain this. So remember this thing. Whenever you have, I mean, for example, you have what other reactions? Like you've studied all these reactions. Let me open a board. One second. Now, for example, you've studied other reactions. Let's see if we have an alkene, right? Okay, let's can an alkene turn into let's say propene. Now you've got this molecule, right? And let's add another carbon chains. Let's say you have CH3 and we've got CH2, and there's this double bond. Now let's say an HBr molecule is coming in and trying to bond with this. So what would happen is, if you know the reaction mechanism, it's going to form a carbocation. Like there's going to be an H and a Br coming in, and there's going to be an H and a Br coming in. Now the thing is that a carbocation could be formed, and the H plus one, like you have an H Br molecule trying to attack it. Hopefully you know what the mechanism is, that the H would get attracted to the pi electron cloud over here, and the electrons over here are going to get repelled. Now what could happen is that the H could decide to bond with the carbon on the right, and this other one would become a carbocation. Now if you look at this carbon atom, it's right now bonded to just 3 atoms, I mean 3 groups. So if it's making 3 bonds, that means it's trigonal planar. You get only 3 bonds. So that's H. There is CH2 and CH3 on one side, and there is CH3 on the other side. So this is fan shaped, trigonal planar, 120-degree angle, and the carbon is positively charged. Now in the next step, the Br minus one would come in. Now the Br minus one could attack this carbon atom from the top, or it could attack this carbon atom from the bottom. In both cases, it would result in 2 different optical isomers, just the way I showed you over here. Give me just a second. So you have to be careful about this thing. So you'll be asked little questions on this. Remember, when the carbon is bonded to 3 groups, it's trigonal planar, and if any molecule or ion is attacking it, it would have 2 options: come from the top, come from the bottom, and that would result in 2 mirror images. Is this clear?
Yes, sir.
Sure.
I said then you have then you have other reactions where I said now these are some problems that are associated with having, I mean, there's side effects, I said possible legal action, and larger doses would be needed because the right type of molecule would be in lesser quantity, so you would need larger doses. Now this one, remember, naturally chiral molecules exist in one type. It's always one type of mirror image that mirror molecule that dominates. So, and then you have stereoselective reactions. So here's an example of, like, if you're doing nucleophilic substitution. Now this was nucleophilic substitution. You can probably see the animation that a CN, I mean, this is probably an OH minus one that's attacking this carbon, which is positive. It's already tetrahedral, and there's a Cl attached. The OH minus one would get attracted to this carbon atom, and when it gets attracted to the carbon atom, it pushes the Cl away. But the way it's going to happen is, so the way it's going to happen is that it's going to push the Cl away, and it always results in one type of mirror image, not 2 types. The Cl minus one, sorry, the OH minus one would always attack from one side, and the reason why it would always attack from one side is, let me draw it over there. I said let me draw it over here. SN1 SN2 explain कर लेता हूँ उसके अंदर what's going to happen. So in SN2 mechanism, you've got a Cl, and let's say you have your entire molecule. So this bond is coming out of the page. Let's say this is CH3, and here you have another group. Let's say there is CH3, CH2, and you've got an OH minus one that's coming in. Now this Cl is partial negative, this carbon is partial positive, and it's an SN2 mechanism. In an SN2 mechanism, the OH minus one would attack right away, and the Cl would get repelled. Now, when this happens, the OH minus one, because of its negative charge, would always attack from one side. It's always going to attack from the opposite side. It's always, I mean, it's going to attack from the side that's opposite to Cl. And when it does that, there's always going to be one type of isomer that would be formed. Well, there's going to be a transition state where the Cl would be breaking off and the OH would be joining in, and all these H and CH3s and CH2, CH3s, they would get pushed to one side, and then the Cl would break off. So the C would now be bonded to OH, and all the groups that were on the left side would now be repelled and would be on the right side now. Okay, why? Because the OH came in from this side, and not only did it push the Cl to the other side, it also, all these bonds that were pointing on the left side now are now pointing on the right side. Is this idea clear?
Ji, sir.
But then if in the same, let's say this reaction was happening using the SN1 mechanism, you always, in this one, you're always getting the same type of optical isomer. But let's say you had SN1 mechanism going on. Now in SN1 mechanism, what would happen is that you had, let's say it's the same molecule. And in that case, you had CH2, CH3, and you've got Cl on the side. Now in SN1 mechanism, the Cl would break off first. And when it breaks off, a carbocation is formed. So the Cl minus one would break off, and this carbon atom would become fan-shaped. Because now it only has 3 bonds. It's a carbocation. There's going to be H, there's going to be CH3, and there's going to be CH2, CH3. All the 3 bonds would try to be as far away from each other as possible, and the Cl would have broken off, and this carbon would be positively charged. Now in the next step, the OH minus one comes in. Now the OH minus one could come in from the bottom, or the OH minus one could come in and attack from the top. So no matter which side it comes from, it's going to result in 2 different optical isomers. So yeah, is that clear?
Ji, sir.
So you don't have to go into a lot of detail about this. You'll get very small questions on this, which you have to remember. Okay, when would 2 different optical isomers be possible? In which reaction? And they'll probably tell you in the question. Okay, they wouldn't let you guess it. They'll tell you. They'll just ask for the explanation. Okay, why are, for example, they might give you this mechanism, and they would then ask you. They won't show you that OH minus one is attacking from the top or the bottom. They'll just ask you, why do you get 2 different optical isomers in this? And they might give you this mechanism. They won't draw the mechanism. They'll just tell you that it's SN2 mechanism. And they'll just ask you, why are you getting 2 different? Only one optical isomer in this case, not the other one. So very little small questions on this. Okay, Mariam, you're not going to get big questions on this. Is that clear?
Ji, sir.
So, okay, let's try and I just picked this paper now. This is a very old paper actually. This is even older. One second. So let's try and do this one. Probably. Okay, let's try and do this one. अच्छा पहले बहुत सारी चीजें miss हो गई. Let's try and do this one. This was March 20. So I'll just try and do this very quickly. Transition element. It's a 1 mark question. What's a transition element? It is when you have. क्या होता है कोई मुझे बता दे. It forms stable ions with incomplete d subshell. So they're basically d block elements that form. I mean, they belong to d block elements, and they form stable ions with incomplete d subshells. Compare the melting and boiling points and density of iron, and you don't have to explain this. So melting points are obviously higher for transition elements, higher for density as well. Then you have complete electronic configuration of an isolated Fe2+, so you can probably do that. Explain the origin of the color of transition metal complexes. So what happens in a transition metal is, okay, why are they colored? Okay, they've got a D subshell. So if there's Fe2+, then it has an inner D subshell. And those D subshells are inside the outer shell. The electrons on the axis, and in the d subshell there are electrons between the axis. Okay, so you've got electrons that are in the middle of the axis. And because the transition metal is a small ion and it has a 2+ charge, in this case it has a 3+ charge, so it has a very high charge density. So all these ligands, they bond on the outer shell. The outer shell is usually empty because the 4s electrons are lost. So the orbitals in the outer shell are mostly empty. So what happens is you've got ligands approaching. Ligands are like water molecules with lone pairs, and because of if they approach on the axis, they've got nothing to do with the D subshell apart from the repulsion that they're exerting. Remember, the ligands are only existing in the outer shell. They've got nothing to do with the D subshell. But because of the presence of these ligands, it would be a lot harder to keep electrons in the d orbitals which are on the axis. So it would be easy to keep electrons in the orange orbitals, but would be difficult to keep electrons in the blue ones. So what would be the explanation? Explanation would be that due to repulsion from lone pairs on ligands, the d subshell splits into 2 energy levels. If it's an octahedral complex, then the ones that are on the axis would be at the higher energy level, because it's much harder to keep electrons on the axis. And the d orbitals that are on the between the axes, it would be easier to keep electrons over there. So due to repulsion, the d subshell splits. An electron from a lower energy d subshell, d orbital, can gain energy and move to a higher energy d orbital. And the energy gap matches frequencies from the visible spectrum. And hence you see a complementary color. You can remember this explanation. It's a very typical question that almost always comes. ठीक है, is this clear?
जी सर.
अच्छा, फिर इसमें
Yes, sir.
the other question would be asked is, okay, why does changing the ligand change the color? Because if you change the ligand, the energy gap, a different ligand would have a different amount of repulsion, and the energy gap that would exist would be different. And since energy is proportional to frequency, a different frequency from the visible spectrum is absorbed, and a different complementary color would be seen. So next is you've got state the shape of so 6 bonds, that's octahedral. So this one is octahedral. Write the equation for the reaction between FeH2O6 and in excess of Cn minus 1 ions. You can see over here that CnB6 and ठीक है, the formula over here. You've got 6 Cns as well. Now you just have to write an equation for ligand exchange. It's going to be FeH2O6. It's going to be 3 plus you've got 6 Cn minus 1 coming, 6 Cn minus 1s coming in. Always remember it's a reversible reaction. Fe and the Cns are changing positions, and this is 4 minus, and this one is 6 water molecules getting knocked out. Now, and this was 2 plus actually. So this one is 2 plus. Now reduce the oxidation state of iron FeCN6. So Cn is minus 1, so that's is plus 2 over here, because Cn is minus 6 and overall it's minus 4, so Fe must be plus 2. Now in the other one, he's saying that there is another ligand coming in, which is NO, and he's asking you to and he said that NO is neutral. So NO is neutral, NO doesn't have a charge, so Cn is 5, so that's minus 5, so Fe must be plus 3, so you get minus 2. Monodentate ligand is the one that has or forms only one dative bond, one dative coordinate bond with a central metal cation. In a complex, in a metal complex. Completed to show the three-dimensional structure of Fe. So that's 6 in total. This could draw it in a three-dimensional way. Then you've got a dotted line. So you've got NO and you've got CNs. And the overall charge is minus 2. Now the two complex ions are different colors. Explain why the colors of the two complex ions are different. So you're going to talk about different ligands. Different ligands would exert a different repulsion on the d subshell, and the energy gap created would be different. So different, and energy is proportional to frequency, so a different frequency from the visible spectrum would be absorbed. You clear? Saqib, is this clear?
Yes, sir. Yes, sir. Clear, sir.
As a coordination number, it's a number of dative bonds that are formed in a metal complex with a central metal ion. Now, E shows both optical and cis-trans isomerism. What is E? E is this thing, C2O4 2 minus and Cl2. And you have to draw in the boxes below three-dimensional diagrams to show. So the trans isomer of E and the optical isomer of E. So here's E given. So what's the optical isomer? What's the trans isomer? The optical isomer is going to be the mirror image of this. Okay, that's the optical isomer. So you have to draw that. Just उसने draw किया उसी तरह draw कर लो. Okay, there's dotted line, this thing. So what's the mirror image? This thing would be on the other side. So it's going to be how would it be mirrored? Cl would go to the other side, so this would be Cl. Okay, left and right would be switched. This Cl would stay there. So this OX would this is a bidentate ligand he's showing. So this OX would, this OX would switch side. So it would be over here now. And there's going to be an OX over here.
Sir, can't we also show trans by having Cl on opposite sides?
I mean, that would be that. Sorry. This one is optical. I think I was drawing optical. No, this one is optical, and this is the mirrored version. Okay, that's the
So
mirrored.
why are we crossing over OX and CL?
Which one?
Sir,
We're not crossing it. Think of it. I mean, OX is over here. The CL is the dotted line that's going into the board behind it.
so why can't we just draw the exact mirror image, like just flip it over?
I mean, that's exactly what we did. I've
Sir,
switched the
the CL
different
that you made here, shouldn't it be down?
Which
Like
one?
the dotted line connected with
नहीं,
CL.
everything should be अच्छा हाँ exactly ये गलत किया ठीक कह रहे हो आप left right switch करना है ना just one second left to right अच्छा नहीं a lot of things I did not switch it left to right उसको literally left to right switch करना है just one second even the OX are wrong फिर से करो this अच्छा एक तो उसने वो भी इस फॉर्म में दिया अच्छा so this is not going to be there क्योंकि left to right switch करोगे this would become this thing so everything has to be mirrored ठीक है अब सही है so everything has to be mirrored left to right so the first thing is you're going to mirror the axis so the axes are now mirrored now start mirroring this this OX would be on the other side it would be over here at this side so this OX would be over here and then you have this CL would be on the right side which should be over here फिर ये CL वहीं का वहीं होगा that's still there and the OX would be ठीक है गलती ये की थी कि एक्सेस नहीं किए थे now it's fine clear है
जी sir.
जी sir.
अच्छा trans is easy कि बस the CLs must be right now they're 90 degrees to each other they must be completely on opposite sides and वो जो बाकी एक्सेस होंगे उसके ऊपर you would have OX ठीक है you can keep an OX over here and one would be over here ठीक है that's your trans version that's the trans version clear है इसमें confusion नहीं
जी sir.
इसमें confusion हुई है most of the time they usually give it like this okay they draw the axis like this उसके अंदर आसान ये होता है कि जब आप mirror करते हो you don't actually mirror the axis क्योंकि the mirrored version of the axis would look exactly the same तो इस फॉर्म के अंदर जो उसने दिया हुआ था ना इस फॉर्म के अंदर the additional confusion was that when you switch left to right the axes also get mirrored ठीक है so अगर वो इस फॉर्म में उसने दिया हुआ है this form में you mirror it so it's not but just understand कि you have to just draw the mirrored
Sir,
version yes
मुझे trans वाले में confusion हो रही है trans में shouldn't like the same type of molecules shouldn't they be not on the same side like यहाँ पे chlorine same side पे है ना
नहीं opposite sides पे 180 degrees
okay
one is at the top the other one is pointing at the bottom ठीक है ये same side है कि 90 degrees ठीक है that's the same side
okay sir
ये octahedral में होता है octahedral में you look at the angle octahedral के अंदर you look at the angle कि it's 90 degrees that's same side 180 degrees opposite that's opposite sides that's the next one so you have C2O4 contains a ligand which sits ethane dioic acid and complete a table to show any observation for the reaction of with the named reagent and where no change is observed write none So this is ethane dioic acid, though it's not an aldehyde, it's a carboxylic acid. And so now ethane dioic acid would react with magnet, would get oxidized. ठीक है, tolerance के साथ it was methanoic acid that would react, not KMNO4. ठीक है, clear है? Oxalic acids and methanoic acid, they both get oxidized, and ethane dioic acid, which is oxalic acid over here,
Sir,
it
this
gets oxidized.
how much more will this oxidize? Like, isn't it already a carboxylic acid? So like,
It
इससे
will turn
ज़्यादा
into
further क्या होगा?
carbon dioxide and water. ठीक
Okay.
है, और वो भी methanoic acid does the same. It gets oxidized to carbon dioxide and water as well. ठीक है, both of them, they get oxidized to carbon dioxide and H2O. और इसका ना एक, क्योंकि लास्ट टाइम भी एक कंफ्यूजन ये हुई थी, इसका ना एक सेकंड, जस्ट 1 सेकंड, क्योंकि एक लेटेस्ट पेपर के अंदर ना देयर वाज दिस कंफ्यूजन, उसको दूर कर लें. Just a second. अच्छा, somewhere in carboxylic acids, 1 second, where's the... Now, oxidation of methanoic acid, Mari, probably you remember this. So it's clearly written, I mean, there's only two carboxylic acids that get oxidized, ethane dioic acid, which would get oxidized with KMNO4, and there's methanoic acid, which is going to get oxidized with Fellings and tolons. ठीक है, लेकिन last time we were doing a paper and in the mark scheme they had also written KMNO4 for this, so it's not given in the syllabus, but in the paper they had actually written KMNO4, or latest ही था 2020 था probably. So just remember that methanoic acid, I mean, there's just two carboxylic acids that you have to remember that get oxidized. But for methanoic acid, apart from Felling and tolons, you can also write KMNO4, because that was given, I mean, that was actually needed to solve the question. So you can add that, even though it's not given in the syllabus. And so now, moving on, where's the... That's this one. State the trend in the thermal stability of carbonates, so it increases down the group. Why? Because ऊपर वाले, can you all hear me? आवाज आ रही है?
जी sir.
जी सर.
अच्छा, so बस जल्दी से इसको orderly कर लेते हैं कि why do carbonates become more stable down the group? Because ऊपर वाले, at the top you have a small ion, you have got greater charge density because of the smaller atomic radius. Down the group the atomic radius increases, so you've got more polarizing power, and what it does is that it polarizes the carbonate ion, and the carbonate ion decomposes, turns into carbon dioxide, and this thing would turn into MgO. Harder to do that when you go down the group. So just 3 points that down the group ionic radius increases, polarizing power decreases because the charge density decreases, and the carbonate ion is less polarized. So the carbonate ions become more stable down the group. And so this one, why? And this is also a very typical question: why do the sulfates become less soluble down the group? Uh, the reason they become less soluble is because the solubility of sulfates depends on two things. If you're trying to dissolve a sulfate and trying to turn it into aquasines, Mg2 plus and SO4 2 minus aquasines, so there are going to be two things that you need to do. You need to break the lattice, so that's the negative of lattice energy. That's an endothermic process. You would have to break the bonds, break the lattice, ionic lattice. And once those lattice bonds are broken and they've turned into gaseous ions, then you mix them in water to form aquasines. So that's enthalpy change of hydration, and that's the exothermic part. So what you're going to write is that down the group, the ionic radius or cationic radius increases. That's the first part. And if it increases, that means the bonds that are broken, they are weak, and the bonds that are formed are also weak. Bigger ions, they form weaker bonds. So both lattice energy and delta H hydration decrease because bigger ions, they make weaker bonds. And since down the group the solubility is decreasing, like because barium sulfate would be less soluble. So why is the solubility decreasing? Because even though both of them are decreasing, both lattice energy and the enthalpy of hydration, they're both decreasing, but the endothermic part is still relatively greater compared to the exothermic part. So delta H hydration decreases more compared to delta HLE or lattice energy, and which is why the overall enthalpy change of solution would become more endothermic, which is why they're becoming less soluble. And you must know this Hess cycle as well. You might get questions related to, like Born-Haber cycle, you also get questions on this. So remember, this is the Hess cycle for something that is dissolving. There are two parts. You break the ionic lattice, and this is for ionic compounds only. You break the lattice, and then you form you dissolve the gaseous ions into aquasines. So the first part is always the same. That whether it's the solubility of the hydroxides or the sulfates, the first part is always the same. Its ionic radius increases down the group. So both lattice energy and enthalpy of hydration decrease. And if they're becoming more insoluble, that means the endo part is still bigger compared to the exo part. So this one is decreasing more compared to this one. So which is why overall enthalpy of solution is becoming more and more endothermic. Okay. Uh, so remember this. Both of these questions, they're very typical questions that usually come in the exam. Okay. The stability of carbonates and the solubility of sulfates and hydroxides. Okay. There's probably a very high chance of these two coming in your exam as well. You clear?
जी सर
जी sir.
अच्छा, now this one वो आ गया Faraday constant वाला question. ठीक है, so this one is, okay, just hold on 1 second. हेलो सलाम, की आवाज आ रही है?
जी सर।
अच्छा
यस
ठीक है
सर।
सर, सॉरी इंटरनेट बंद हो गया था, जस्ट वेट 1 सेकेंड। अच्छा जस्ट अ सेकेंड। चलिए दिस वन, अच्छा दिस वन is अच्छा this one is an interesting question कि aluminum is extracted from aluminum oxide and Al2O3 is dissolved in cryolite in the process, and he's saying that the half equation for the reaction at the anode is given. Use this half equation to write the ionic equation for the electrolysis of Al2O3. So you've got to write the equation for the electrolysis of Al2O3 using this equation. First thing is, if you remember Al2O3, it has two ions, Al plus 3, and you've got O minus 2. So this is what's happening at anode. So what would be happening at cathode? Cathode ke upar you will have Al plus 3, that would be gaining 3 electrons, and it would be forming aluminium. So that's your equation at cathode. Now remember, he was asking for the overall equation. How do you write the overall equation? The first thing is you balance the number of electrons that are lost and gained. So the 2 electrons lost and the 3 electrons gained, they must be made equal. So I'm going to multiply the first one by 3. So everything would be multiplied by 3. And this one would become 6. And this other one would be multiplied by 2, so that this 3 becomes 6. And I'm going to add up the reactants and the products. So it's going to be 3O minus 2 plus 3C plus they're going to be 2Al plus 3. And on the other side, you've got 3CO plus 2 Als. So this is what's going on. Now, aluminum oxide is electrolyzed for 3 hours and using carbon electrodes and a current of 3.5 into 10 to the power 5 amperes. Calculate the mass of aluminum that is formed. So you've got Q is equal to IT. You do that first. Find the total charge that's passing for 3 hours at this current. So it's going to be 3.5 times 10 to the power 5. And that would be multiplied by 3 hours. 3 hours is 60 minutes, and every minute has 60 seconds. Mariam, can you do the math?
Sir, I'm getting 3.78 into 10 power 9.
That's a 10 power 9 coulombs. So you've gotten the total charge that's passing through the circuit. Now the next step would be to convert that into moles of electrons, and for that you would use the Faraday constant, which is that 1 mole of electrons has a charge of 96,500 coulombs. How much charge is passing through your circuit? That's 3.78 times 10 power 9. So how many moles of electrons is that? So X would be equal to 3.78 times 10 power 9, and that is going to be divided by yes, 96,500. How many moles do you get?
Sir, I get 39,171.
How much? 30? Can you repeat the number? कितने thousand था?
Sir, 13,171.
So I just heard 38,171. Is that right?
Sir, 39,000.
I said 39,000. So we're getting 39,171 electrons, moles of electrons, right? So that's the moles of electrons. Now, we know that how many electrons were needed to deposit one aluminium? That was 3 electrons, right? So based on this ratio, yeah, you divide by, because we've got 3917 moles. We've got a lot of moles of electrons. So the moles of aluminium would be 1/3 of that. So what's 1/3 of this?
Sir, 13,057.
So that's 13,057 moles of aluminium, and you can
Sir, why are
multiply
you
it by,
taking 1/3 of aluminium? Moles?
क्योंकि हमने अभी निकाला कि we found the moles of electrons, right?
Right.
So 3
Right,
electrons,
okay, yeah.
ठीक है. अच्छा खैर into 27 करो, AR से multiply करो, you'll get the mass, ठीक है? That would be the mass of aluminium.
Sir, it's 3.53 into 10 power 5.
3.53 into 10 to the power 5. That's the next one is cryolite can be made from SiF4. The first step in the conversion is SiF4 with H2O forming write an equation. So you can write an equation. Everything is given. हाँ इस पे कोई problem नहीं होगी. Next one is you're given. Okay, define the term standard electrode potential. So it's the potential difference. And remember word standard use हुआ है, ठीक है? तो उसकी भी reference देनी है. What is standard? So it is the potential difference between a standard electrode and a standard hydrogen electrode. So that's the potential difference measured under standard conditions. So यहाँ पे ना you give the reference of what is standard condition measured under standard conditions, and you can quote what those conditions are: 298 kelvins and 1 atmosphere pressure, etc. 1 mole per dm cube if it's a solution. So draw a labeled diagram of the apparatus that should be used to measure the standard cell potential. Include all necessary chemicals, and now you've got an EU3 plus and AU. So remember the 3 types of electrodes. There's an electrode that involves a metal. So if it's a metal, then the metal is the electrode. So it's AU, and the ions would be in the solution. So there's going to be AU plus 1. Sorry, not AU plus 1, AU3 plus aqueous. So they would be part of the solution. That's one of the electrodes. The other one would be, the first thing is we would have to figure this out. Although everything is given, it's a gas. If it involves a gas, then there's going to be a gas jar. And the NO gas is going to be at a pressure of 1 atmosphere. Remember to write down the concentration. AU3 plus aqueous would have a concentration of 1 mole per dm cube. Anyways, you've got NO as a gas, and that NO gas would be, and there's nitric acid. So nitric acid would obviously be part of the solution. So there's HNO3 aqueous, and that's going to be 1 mole per decimeter cube. Now the only thing left is you would need a catalyst. Okay, gas while electrodes, it's always a catalyst that's needed. That's going to be a platinum catalyst, and you're going to have voltmeter connected to it. The platinum is going to be the electrode. Plus, there's going to be one thing that's required. That's a salt bridge. Okay, the purpose of the salt bridge is to complete the circuit. So that's and pretty much everything is labeled. Just label this properly that it's a platinum electrode. This is a gold electrode. So everything is labeled. Now, what you're given is, you're saying write an ionic equation to show the spontaneous reaction that occurs when an electric current is drawn from the cell in A2. So you're saying the spontaneous reaction that happens. So you've got an AU electrode with Au ions. That's the first one, right? And you've got NO and NO3 like nitric acid. That's H plus 1 and NO3 minus 1, and there's NO gas, right? So there's this electrode. So what's the rule? Who's going to gain electrons and who's going to lose electrons? क्या होता है?
Sir, higher E naught gains, lower E naught loses.
So it's going to be the first one gaining and the second one losing electrons. So you have to write the ionic equation of the spontaneous reaction. The good thing is that the number of electrons lost and the number of electrons gained, they're equal. So you don't have to multiply any equation with any number. So add up the reactants. पहले वाले में reactant is Au3 plus. And in the second one, the reactant is this one, NO gas and 2H2O. So it's NO gas. You can write the states 2H2O. And the products in the first one is Au solid that's forming. And in the second one, it's NO3 minus 1 aqueous. Plus 4H plus 1 aqueous. Or in Kiwi states, like it's this one is aqueous, this one is gas, or this one is liquid. And calculate the E naught cell for the reaction. So that's higher potential minus lower potential, or reduction potential minus oxidation potential. So 1.50 minus 0.96, and that gives you 0.54 volts. तो ये भी हो गया. और इसके बाद he's now saying gold can be oxidized by a mixture of concentrated hydrochloric acid and concentrated nitric acid known as aqua regia. Concentrated hydrochloric acid is 12 mole per dm cube and concentrated nitric acid is 16 mole per dm cube. So you can see that the concentration of the acid is really, really high. Explain why aqua regia is able to resolve gold. In your answer, state and explain what effect the use of concentrated hydrochloric acid and concentrated nitric acid have on E values of half equations 2 and 3. So there's something happening to equations 2 and 3. Go and have a look at equations 2 and 3. So now you can clearly see over here, first thing, okay, this is a spontaneous reaction happening. In the spontaneous reaction, note one thing, that gold is not dissolving, gold is actually forming. I mean, it's not happening the other way around, that gold is turning into aqueous ions. So the spontaneous reaction is that the reaction, gold does not dissolve, gold is very unreactive. And the spontaneous reaction clearly shows that the ions are turning into gold, the gold is not turning into ions. So spontaneous reaction suggests that it does not like to dissolve. Okay, is that clear?
Yes, sir.
So the spontaneous reaction is suggesting this. So what happens if you use, let's take 2 or 3. So I'm going to rub all of this. Now, if you use concentrated nitric acid, like a very concentrated nitric acid, so it's going to have a lot of NO3 minus 1 and a lot of H plus 1 ions. Where would the equilibrium shift? The third one, right or left?
To the right.
Right.
It's going to shift to the right. And if it shifts to the right, then the potential increases. Remember, if it shifts, whenever your electrode equation shifts to the right, the potential increases, because it would gain a lot of electrons and the electrode would become more positive. So let's say it has increased to, क्या value होनी चाहिए? Let's say it increases to 1.55 volts, just hypothetically speaking. It increases. Now what would happen to this second one? So let's focus on the second one as well. Let's say let's talk about this one. Let's say the Cl-1 concentrated, because you're using concentrated HCl. So if the Cl-1 concentration increases by a lot, the equilibrium would shift backwards, right? It's going to shift backwards. And if it shifts, because the Cl-1 concentration is increasing, so if it shifts backwards, the potential would decrease, right? Let's say it decreases to 0.6 volts. Okay, just hypothetically speaking. So why does gold dissolve? The gold would dissolve is, the reason gold would dissolve is, this one would become your higher potential, and this one would become your lower potential. Okay, because the values are going to change. If you use a very high concentration of nitrate and H+1 HNO3, it's going to shift in the forward direction and the potential would increase. And vice versa, if you use a very high concentration of Cl ions, the equilibrium would shift backwards and the potential would drop. Now, if you compare the two, or compare all the three, the highest potential is the bottom one, and the lowest potential is for the second one. So your new reaction is going to be, let's write the new reaction. Again, we are lucky that the electrons are already balanced. Now add up the reactant, so it's Au solid plus 4Cl minus 1. And the other one, the reactants are NO3 minus 1 plus 4H plus 1. What about the products? In the first one, the products are, it's a complex sign, AuCl4 minus 1. And in the second one, the products are NO gas and 2H2O. So you can clearly see that it's dissolving. Complex ions are always formed in solution. So Au solid is turning into AuCl4 minus 1, and this is the reaction that's happening. So आपने पूरे answer में you have to explain this. That if you write this equation, tell them that if you increase Cl-1 concentration, the E0 would drop. It would become lower. And if you increase nitric acid concentration, the E0 would increase and it would become higher. And the two would start to react with each other. And this would be the overall equation, which is why gold would dissolve. TK, is this clear?
Yes,
जी
sir.
sir.
Achha, next is, so 3 marks for this. Next is about rate of reaction. Write an equation and determine the rate of the. I said, to figure out the rate equation, you would have to. 1 second. I said, now to figure out the rate equation, you would have to figure out the order of the reaction. जो कि उसने नहीं mention किया हुआ कि नहीं, this is aqueous gold 3 reacts with aqueous H2O2 under certain conditions. So these two are reacting, and AuO2 and HCl is produced. So this is being produced. They've pretty much given everything. So it's AuCl3. First line के अंदर AuCl3 plus there's H2O2, and the product is क्या क्या दिया हुआ? It forms AuO2 and HCl. अच्छा, now in this case, AU is gaining. इसको वैसे ही balance करो. It's going to be 3 by 2 Cl.
Sir, it's H2O2.
So this one. अच्छा, H2O2. अच्छा, so you've got AuCl3. अच्छा, पता नहीं इसकी बैटरी बंद हो जाएगी, फिर खुद ही क्लास खत्म हो जाएगी अभी. You've got AuCl3 and you can balance it. इसको 2 कर लेते हैं ताकि Cls balance हो जाए 3. So you've got 6 HCls and you've got 3H, so that's 3H2O, and you've got सब कुछ balance चल रहा है अभी तक. There's going to be 6 oxygens, so that's 3O2,
Sir,
right?
2AU होगा आखिर में.
2AU, that's the. ठीक है. Now the only thing you have to check is whether the equation is balanced or not. In the sense that the number of electrons gained, and it's a redox reaction. उसका ख्याल कर लेना, ठीक है? कि AU is +3 and over here AU is 0, so that means a gain of 3 electrons. But since there are 2 AU, so that's a gain of 6 electrons. Either oxygen kya hai? Oxygen is -1, and over here oxygen is -2, or oxygen is 0 actually. It's 0 over here. So अगर वो 0 होगा, that means -1 to 0. That's a loss of 1 electron, and there's 6 oxygens, so that's a loss of 6 electrons. So electrons equal hai. Always be careful about this, okay? Whenever you balance an equation, it's a redox equation. Make sure that the number of electrons gained and lost are equal. अच्छा, अब इस case में what you have to do is you have to find the order of the reaction. How do you find the order of the reaction? इसका order निकालना तो 1 और 2 को compare करो, so that's easy. H2O2 is not changing. This is doubling, so that's into 2, and you can clearly see what's happening over here. That's I think is doubling. ये double ही है ना. Calculator से check कर लो कि divide 1.53 into 10 to the power -1 by 7.66 into 10 to the power -2, you'll get the factor. So same ratio. So that means order with respect to AuCl3 is 1. Is this clear?
जी sir.
अच्छा, दूसरे का निकालना मुश्किल है, तो उसके लिए आप क्या करोगे? What you'll do is, अच्छा, why is it difficult for the other one? Because क्योंकि H2O2 का अगर निकालना है ना, what you would have to do is you would have to find reactions in which H2O2 is changing but AuCl3 is constant. But you can see there is no place where AuCl3 is constant. So what are you going to do? What you're going to do is pick any two random reactions in which this is changing